discussion we are sharing, that is, inside our brain. So human brain, usually we know that we have talked about prefrontal cortex in the last day. So basically we know that now this prefrontal cortex is associated with some kind of thinking, or some kind of logical part, or some kind of decision making part. I can say the frontal part and the prefrontal region. That is, yes, I can say that is, yes, it is, everything is all right. And or we can say that no, I think a little bit is missing somewhere, everything is not okay from my side. So this is a kind of evaluation that is basically based on some kind of cognitive task, or some kind of information processing that is happening inside the hippocampus and the amygdala region. As you can see that this hippocampus regulates the memory and the emotion. So memory is nothing but the storehouse, I can say, of every kind of emotion, or I mean emotions, every kind of information, whatever we are gathering from the environment, whatever we are in process of daily lives, whatever we have learned through our from our, since our childhood. So all those information is stored in the memory. And also the amygdala portion, which basically turns on fight or flight, and stores memory of the event. That means these are the kind of strong areas of the human brain. Because what happens that whenever there is a sense of conflict, there is a between a conflict between what we nurtured from our childhood and what we are now getting from the environment. So if there is a conflict, the amygdala turns on, and it basically wants to store the particularly explicitly exclusive event of the current scenario, along with whatever we have in our storehouse, whatever be the permanent memory we have in our storehouse. So what is a weak region? Weak region is, you can see that the pathways from prefrontal cortex to hippocampus. That means this area. Why so? Because what happens that we are usually dealing with some kind of, what should I say, some kind of the temporary data. That means some kind of dynamic data. That means, yes, now you need to perform certain kind of mathematical sum. So you can you can easily, you can readily add two numbers, and you can give the results. Whenever this particular process is going to be completed, you just automatically erases everything that what you have done, and you just you will jump into the next problem, right? And again you start adding between two numbers. So this is a kind of weak part, where it is going to be involved into very strong cognitive process, that is a decision making process. So, if this is the functionality of the human brain, then we can, categorize the subsystems of the human memory. Because if I want to highlight about the problem of dealing with the cognitive load, that means this load must be created inside the human memory, inside the brain. Obviously it is dealing with the human memory. So what could be the subsystems of the human memory? Here we can see that here we have some sensory memory. The left part of this is the green boxes, and the, you can say, the peach colored boxes. Those are the sensory memory. Sensory memory means whatever be the information you can get from the multimedia presentation, or from the sensory organs. So either you can have any kind of multimedia presentation involving some kind of words, some kind of images, some kind of music, some kind of this kind of things, just like that what you are getting right now, right? So this is your now sensory information, and it is basically related to your sensory memory. So whenever you have got this kind of multimedia presentation, that means the combination of words, combination of pictures, combination of images. So all those sensory informations are fed to your sensory organs, and we know that the sensory organs are ears and eyes. These are two prime sensory organs, right? So the person starts sensing what? The sensory information. Whenever the sensory organs are going to identify all the sensory informations, then these sensory organs tries to select the words or the pictures which they need to feed in the working memory, where we are going to paste those or create the impact of those words and pictures, so that our working memory starts activating. So automatically ears are collecting some words which produces some kind of sounds in our working memory. Eyes can select the pictures or images, and automatically it create an impact of images in our brain. So working memory, what happens that using those sounds and images, maybe it may happen that at one particular point of time, it is coming into the working memory in the jumbled order. So working memory has this capacity to organize those words, organize those sounds, organize those images or pictures, so that it can formulate some kind of verbal as well as pictorial model. And whenever this working memory integrates those two models, and it starts the processing of these two models by integrating some of these sounds and images, then it starts it starts to process any of two actions. One action, it could be that it tries to now infer or tries to now create a new decision, a new confirmation, a new conclusion, and that could be that can be stored into the long term memory for for long term use. Or somewhere in during this process of integrating, it finds a certain kind of help. It finds to take certain kind of help from whatever be the prior knowledge we have in our long term memory, so that we can match these two information, that is the current information, with one we already possess from since our childhood, or since past 2 or 3 years maybe. So we need to match those two informations to take the decision, to take the final call, that what kind of the final impression which we can develop by using this working memory. So there you can see there is a kind of integration takes place by helping also by taking help from the prior knowledge as well, from the long term memory. And this synthesis or this integration part happens in the working memory. Why does this you know happen? Why this working memory tries to take help from the long term memory? Or whenever it processes something, why this working memory tries to shift this particular conclusion or the decision to the long term memory? Why this is so happen? Because the working memory has limited capacity. Even if the working memory has the best efficiency, because the whole process is going inside the working memory, still it is having limited capacity, so it cannot store a very large amount of information. So it needs to to clear up the cache, and it wants to create some free space, so that it can process the next information what is coming from the sensory memory. So this is how the subsystem of human memory is segregated. Now, whenever we have these three type of memories, then you can see that this sensory memory, what I have just, described, that this sensory memory has the incoming information, right? And this sensory memory can hold information for only 1 to 2 seconds, right? And it basically does not reach consciousness. What does this mean? This means that whatever be the working process that the sensory memory is holding, that does not refer that the that does not give you no give you a strong reference that the person is in conscious state. Why? I have just told you that whatever be the process that basically the sensory memory is performing, like, in case of, that kind of thing, that means it is just only, catching all the or receiving all the sensory information from outside. That means either from PC, either from laptop, either from, from the environment. So basically it is just only, receiving those information, and it is only just passing to the working memory. Once it passes those information in the working memory, it is simply, forgotten, whatever it is, passed. So automatically, based on the performance of the sensory memory, I cannot say that a person is in conscious state. For this, we need to, go further with the working memory and long-term memory. Whenever we are going to working memory, so this working memory has the capacity to hold information for a few seconds, but what happens that this is a kind of memory which is every time in process. Some kind of encoding must be there. You can see that some kind of encoding must be there with the long term memory, or some kind of, working memory finds some kind of, tendency to fetch some information from the long term memory, which is here addressed as retrieval process. That means the information retrieval process must be going on between this working memory and long term memory. So it is a kind of thing, there is some kind of, tendency to basically to pass on some kind of, information to long term memory as well. So whatever be the information that the working memory is getting from the sensory memory, it can hold for a few seconds because it starts, processing with those information. And if we are not going to, make this working memory rehearsed, then at about, after at about 20 seconds, you can see that this working memory is already, forgotten what the, information it is basically, getting from the sensory memory. So in that manner, I can say that this working memory can hold information. It's a, good sign, but it almost, lost the information after at about 20 seconds if not rehearsed. Now, whenever this working memory passes all the information, what, before, losing, or before, forgetting about the processing, whenever it passes into the long term memory, so this is something which holds the memory, which holds the information permanently. So it is a permanent form of memory, which basically, establishes, you can see, the meaningful connection between information. That means there is a kind of information processing, either encoding or retrieval, so that we can make a, concrete decision about the information what we are getting from the outside environment. And also, you can see, since this is a long term memory, so automatically it is acting as a permanent storehouse of the information, I can say. So from this particular storehouse, the information can easily be recalled. So I can say that if I, if I go on looking about the working memory and the long term memory, I can, if those two, give me the, the better, recall, better retrieval of the information, better encoding process, then I can say at least the person is a little bit, conscious. So the consciousness, basically, depends on this working memory or long term memory, but not, in the, I mean, not on the sensory memory. So this is the relationship, I can say, between the sensory, the working, and the long term, memory. Now, so whenever, this particular, picture, whenever I can see, so every time, it reminds me one article written by Daniel Miller and edited by Matt Klein, that, every time what happens that if if I say that my brain is active, then automatically this all the sub parts, all the every inch of brain, is associated with some kind of information. Because that is why we are saying that an active brain cannot be empty one. So basically, you can see that, if I go on, looking at every compartment of the brain, so all the small, every bit of it, deals with certain, our consciousness, or certain, our, sense of being. I can say that sometimes it is, the one small region, one small part is dealing with the appetite, one small part is dealing with the time, small part is dealing with the causality, spirituality, hope, cautiousness, everything. So self-esteem and firmness, and you can see every kind of, situation, what basically, and also the friendshipness and everything you can see. So basically what happens that this is how our human brain, behaves, that even if I am delivering my speech, some of my parts of the brain is, subconsciously dealing with any of this, you know the any of this attributes, I can say. So this is, in such process that sometimes we can, hear that my brain hearts. What does this mean by my brain hearts? So let us see, what does this actually mean. So whether you have, reached at any point of time, that whether you realize that at any point of time, that if I put one more detail in my brain may explode. Have you ever, experienced this kind of, stress in your life? So if you are ever experiencing this kind of, stress, that means your brain is experiencing cognitive load, right? So basically what happens that if you take an example of this faculty development program, right? So basically on the very first day, what you were is, you were just, pouring whatever be the lecture session, whatever be the thoughts and ideas we are going to share with you. So what are the concepts you are getting through this FDP? So you just started to pour all the thoughts. By the day is passing by, you are just, pouring, a bit, a bit more, right? So you can see the, the information, is going to be, enhanced within you, within your brain, right? During this FDP, and which always, pointed out in a particular domain, which is dealing with artificial intelligence and robotics. So basically what happens that after the 5-day program, how the, you know our beloved coordinator has designed for us. So basically, after 5 day, you are in a particular point where you have, more and more and more information. Let's say, almost every possible information about this artificial intelligence and robotics, and you are just, you will be, in saturation mode. So what happens that after, let's say, after a certain period of time, you sometimes you feel that if I put one more detail in my brain right now, so my brain may explode. So what happens that if you try to do so, sometimes it may happen that you can see, that you can feel that there is a sense of, losing some information again. That means, even if you have tried so hard to put everything in your brain, so now if you want to, compress your brain, you know, farther, so to put any further details in your brain. So maybe you start feeling that you may be, losing some kind of, information. That is, some kind of information is going out. So this is something we call in our artificial intelligence domain, that this is, cognitive load. So the cognitive load is nothing but the total amount of mental effort used during the completion of task, right? So if you are not, feeling any kind of mental effort, if you are not going to, put any kind of stress by, by completing any kind of task, you are in balanced, condition. That means your cognitive load is, a balanced one. But if you are feeling this kind of, stress by doing so, if you are feeling some kind of mental effort, if you need to put, extra effort, that means you are in, higher cognitive load. So if that is the cognitive load, then what does this cognitive load theory tells us? Cognitive load theory tells us that there can be, three types of load. Three types of load is basically, one is intrinsic load, another is, you can say, germane load, and the third one is extraneous load. So what could be the intrinsic load? Intrinsic load means, that means you are now such a full, full contained, phase, I mean, full contained brain states, I can say. So, if now you are getting any kind of new piece of information, then you find complexity to basically process that new information. So, this is one kind of, load which is called intrinsic load. That means you find complexity in new information. That means your brain is now barring to, receive any kind of new information. So this is called intrinsic load. Now let's talk about germane load. So germane load means, now even if you are not, feeling right now barred from getting the information from the environment, but somehow whenever you have received those information, now you are finding some kind of problem, some kind of difficulties to link that new information with the current information. So where does this current information is stored in your long term memory, or sometimes, it is in process inside your working memory. So you need to fetch this information, right? Because sometimes you need to compare, you need to match those information, whatever is stored in your long term memory, or whatever is just, is in process, is in, duration of process, just before, a few instants. So you need to find, a kind of linkage between this new information with the current or with the existing information. And sometimes, you are you are finding difficulties to establish that linkage. This is called germane load. Coming to the third load, which is called extraneous load. Those load are basically, created from unnecessary and distracting information. What can be those kind of information? I have just mentioned. I don't know, probably you have heard, any of you have heard or not. Some kind of, carpentry work is going on just, just half an hour before in my nearby places, in the neighboring flats. So basically, one kind of, that carpentry, that a specific, wooden sound whenever you are going to hammer on something. So basically, that kind of, sound, sometimes it is coming. So it creates a kind of disturbance, it creates a kind of distraction in my mind, right? So, whatever be the process I am working, my brain is working, working memory is processing or working on. If this particular, distraction, or this particular distracting sound, this is a kind of information, this is a kind of sensory information, so this creates a kind of load. right? Load in our in my process, in my delivering of lecture. So this creates an extraneous load. So cognitive load theory always tells us that whatever we do, in the process of, you know, work workplace, or process of, working environment, these three loads do exist. So what could be our idea of, you know, balancing the cognitive load? If we give, if you were given this one situation, this is a situation number one, you can see that the person, is standing midpoint. It is basically, try to balance the cognitive load. And what does he find? He find that here, in his right hand, there are three kinds of cognitive loads. One is intrinsic, another is extraneous, and the third one is, germane load. So, and these are, you can see these are all are very heavy, all are very heavy, right? Whereas in the left arm, he is, just holding his processing capacity, the processing capacity of his brain, right? And you can see that those are very small, because working memory is very small. It is having a very less capacity, right? So basically can't squeeze very much. We cannot squeeze our, working memory very much. So basically working memory has a very small capacity. We need to do all the processing, with that particular restriction. Whereas, long term memory is not being used for several times. If that is a situation, that means now this person is experiencing a particular situation where he is thinking that he is going to be cognitively overloaded. And when does this cognitive overload occurs? It occurs when cognitive load overweights or outweighs your processing capacity. So obviously, for every one of us, this must be, a very unavoidable. A very, annoying. A very annoying situation for us, right? We do not exactly want, this particular situation to occur in our life. So what could be the better solution? I can give you, a much better situation where you can see a person is standing, and sometimes what happens now, he, finds a solution to overcome his cognitive overloading situation. What kind of solution he basically, works in? He tries to now maintain the German memory as it is, but he tries to, you know little bit, lesser the intrinsic memory. That means intrinsic cognitive load, this intrinsic load. He is trying to minimize it. How? He, wants to, he is in process, to shift some of its, knowledge, which is basically, related to the intrinsic cognitive load. He is trying to shift those knowledge to long term memory, so that whenever he wants to use, this particular, knowledge in further, due course of time, he is going to fetch that particular information from the long term memory. So you can easily see that as compared to the previous slide, your long term memory is getting bigger, right? Because now long term memory is getting used to access same kind of, knowledge more than once, very often. So in that very manner, and he also is in process, to, to provide the better, environment, better presentation of the information, which basically falls under the extraneous load, extraneous cognitive load. That means he tries to minimize the distraction, he tries to minimize the, those unuseful information, so that he can balance between the cognitive load and the processing capacity, right? Because short term memory is always small, it has always the less capacity. So, in this manner, he tries to balance his cognitive load, and cognitive balance, occurs when there is sufficient processing capacity available for required load, because you cannot avoid load in our present scenario, in our present workplace. We cannot avoid we cannot avoid the problems, we cannot avoid the situations, we cannot walk through. So we have to face, but we need to balance, we need to find the solution so that we can balance between the cognitive load and our processing capacity. So, in this manner, so what are the mantra to balance cognitive load? So, first one is we need to minimize extraneous load. We may need to minimize the distraction, right? So that it can, it can distract the learners. And obviously, to make the learning process difficult, we need to minimize that particular load. We need to maximize German load. That means we need to design our process of learning so well. We need to incorporate proper techniques, proper tools. We need to learn those. We need to keep in our mind, keep in our storage, keep in our storehouse, so that whenever we need to operate, or we need to use those useful tools and techniques, we can fetch from our long term memory, and we can facilitate an effective learning process. And due to this minimization of extraneous load and maximization of German load, we can manage intrinsic load, which is basically which refers to the inherent complexity of the learning material. Because you cannot you cannot do much to reduce this load, but it can be balanced, right? Because this is a kind of load where you may may want to compare, or may want to link every time, every often, the new information with the existing one. So you cannot do much more with this kind of load, but you can balance this load by either minimization of extraneous load and maximization of German load. So this is the key key points to get a balanced cognitive load. Now, if the load is getting balanced, now the question is, can we detect the cognitive load? Can we measure the cognitive load? The answer is yes. So now the question is, how to detect the cognitive load during a task? So if I were given a particular cognitive, a particular task, cognitive task, and if I want to measure that what is the level of cognitive load during this task, we should, take into consideration certain points. So these are the points, what we need to do, we need to follow. First of all, to classify the difficulty level, that means if I want to measure the cognitive load during a task, I, I need to design that task into different difficulty levels, right? Because if I follow only one difficulty level, if I want someone to, perform a task with easy, with easy problems, then how can I judge whether the person is able to take the cognitive load more or not? So I need to design a particular problem with, different, difficulty levels. And obviously, the state of inactivity during a mental, arithmetic task, or mental problematic task, or mental logical decision making task. Here, in this particular problem, we have taken, consideration of a mental arithmetic task. You can take a logical decision kind of task, aptitude kind of task, the this, or non-verbal reasoning kind of task as well. You can take these also. So if you are designing this kind of environment, this kind of problem statement, then you can gradually shift the difficulty level of the problems, the logic, be it the logical problems, be it the arithmetical problems. You just go on increasing the difficulty levels from easy to harder or more harder, and finally you can, you can become in the, you can give the problems to the human subjects, with a hardest, difficulty level. So you can do that. And also, whenever you are doing this thing, whenever you are performing this thing, the cognitive load of a subject, is going to be measured during this experiment. So whenever the cognitive load of a subject, you can see here, is going to be measured, for each and every, particular task, then you can formulate a table. You can formulate a table for each and individual subject, that yes, this problem is given to him with this difficulty level, let's say easy, and what is the cognitive load, what is the cognitive, what is the measure, or what is the metric, or what is the value we are getting, so that we can, identify that the person is having cognitive load, say, low. Now at the second instance, suppose the, the subject is given the medium, or the, a little bit harder, problem, and you can, put the decision by watching the metric of the cognitive, load, so that you can comment on the particular, level of the cognitive load during the processing of that a little bit harder, problem, for that human person, that now he is experiencing, a kind of medium cognitive load. So this is how the idea of detection of the cognitive load during a task using artificial intelligence. Now the question is, if I want to do so, we need to make some kind of, stimulus. We have discussed about stimulus. We have discussed about stimulus in the previous lecture as well. That stimulus is nothing but, it can be, a kind of, visual one, it can be auditory one, it can be olfactory one, right? It can be tactile one, it can be a motor movement one. So we need to design some stimulus. Stimulus means which basically, going to feed to the human subject, so that there is a, cognitive task is going inside the, human brain, or I can say the brain of the human subjects, who is basically under the experiment, right? So here, for this particular, problem to detect the cognitive load of a human person, we have made certain arithmetical problems, mental maths, right? Yeah, we have dealt with mental maths. So you can see there, a list of, a very long list of visual stimuli, because we have given all those visual stimuli, all those, arithmetical problems in one set, and we refer to that set as the easy set. We are picking, all those numerical problems which are easy in nature, which are, we are placed in the form of ppt, right? And on each slide, like that, just what you are seeing here, that in one slide we are putting, one particular problems, which basically deals with the mental maths, and obviously we are giving some kind of, stipulated time to solve these things. And if we are going to, the some kind of, cheats over there, that is, which is given in your, that is, one cheat is, referring A, another cheat is referring B, the third one referring C, and the last one is referring D. That means those cheats are referring the options of the, answers. So basically, without moving so much, because we know that whenever we are dealing with this, brain signal communication, brain computer interfacing, a slight movement also, inculcate some kind of noise, you know, in your useful signals. So we just made the person, sitting to, to keep their hands on the table, and near his or her fingers we have placed the chips, so that there must be, the minimum, the most minimum movement to just point out that particular sheet which he or she thinks the, probable correct answer. Fine. So this is how we have designed the experiment. So there, since there is a this is a vast list, I cannot, here it is very much, difficult to show you the whole list of, PPT, even if I have in my PC right now. But I need to, show you that this could be the example of visual stimuli used in experiment for your better understanding. That you can see that the question is, which of the following number is closer to 1.667? So this is a kind of, mental maths you can see. And if you can do the mental maths, for the first option it will give you 2, right? For the second option it will give you 1.667, you can say. For the third option, it's 12 by 9. That means it gives you a 1.33. And for the fourth option, that is for 10 by 7, it gives you the 1.42. So which one out of this following number closer to 1.667? So automatically the correct alternative is option B. So we need to, observe whether the person can, put or can tap his or her finger on the cheat which is mentioning option number B, because we know that the correct alternatives, which one is correct alternatives, right? Now we are going to match whether the person is going to be able to, you know say the correct alternative or not. How much pressure he or she feels to solve this mental maths during a stipulated time period. This is how the experiment is designed. Now, if you, so automatically, you can do this particular experiment, for a number of times with one particular subject, over the different subjects, by combining, or by, showing them, different problems coming one after another, you know, with one particular different slides. As you can see that this is question number 2, out of this, 20 or 30, examples. Now, after completing this set, you have got something, you know, the experiment is going to be performed. I mean, experiment is completed with some easy mental maths. So automatically you should have, a kind of, database which is, from your brain signals, that yes, those are the database we are going to process during the, experiment, related to the easy visuals, easy mental maths, this kind of visual stimuli. Now if you go on increasing the difficulty of the mental maths, then automatically you can give the same person, mind it, or the, over the persons as well, because you need one large database. I have talked about the EG database, or, I am talking about the different kind of, system for capturing these brain images, today. So basically, whenever you are dealing with brain computer interfacing experiment, you need a large database. So automatically, again, whenever you are giving the moderate, difficulty leveled arithmetical problem or mental maths to a particular person, or to the different person to make that particular database. So you can see that here the problem is given that x plus y equal to 22, and x, the product of xy equal to 120. So what could be your correct alternatives? So automatically you can see that 12 and 10, this is basically the correct answer. So within the stipulated time period, and since we are going to make the difficulty level harder, and obviously there should be a kind of, time constraint. So automatically you are feeling some kind of pressure. Now, if you were so good at maths, then automatically, still now you're not going to, feel any kind of cognitive load. Most of us cannot feel the cognitive load till now, right? Now, what happened? That whenever you have got this kind of, answer, and you will have again the set of this kind of moderately difficult leveled, mental sums, like a bunch of that 30, questions, and you have performed the experiment in that manner. After then, you are increasing the difficulty level a bit harder, right? And you are giving a particular, you know, example, a particular numerical example, which can be treated as harder out of these three. That is, if I multiply 6 with this x, it will give me 234. Now the question is, what could be the possible correct answers among these four which give you this result? So automatically, this is the one kind of set of, we have, you can see we have reached a little bit, harder part. We are dealing with the, a little bit time constraint situation as well. So automatically you feel, you feel a little bit, edgy right now to basically, complete this particular cognitive task. Here, cognitive task, I want to mean that to solve this particular mental problem, right? Where I can see that the 39 is the right answer. Why it is called some kind of, difficulty? Because every time our brain is, wired in such a way that we try to, multiply the 6 by the last digit or by the second digit of the correct alternatives, right? So that it will return me a 4. So if anyone returns me 4, then it would be easier for me to basically point it out that this could be my correct answer. But here, why it is called a difficult situation? Because you can see every number, if multiplied by 6, it gives you last digit as 4. So you need to perform the whole multiplication and you need to cross check all those answers, in certain stipulated time period. So the cognitive load is getting higher. What, you know you can feel at the, for the during the previous two experiments. So these are the examples of visual stimuli you can design during the experiment. We have designed and we have got the good, results. So you can do as well. Now the question is, whenever we have done with the, you know experiment part, we have designed also our stimulus. Now how could we process to capture the brain signals, which is the, the interesting part of artificial intelligence. Now you can see that in the previous two sessions, I have talked about electroencephalography, EEG machines, EEG device. In the first, session, I have talked about the use of, you know, standalone EEG machines for a problem. In the second session, I have talked about the use of wireless emotive headset for a different kind of cognitive problem. Here, I'm going to show you the use of the another device which can be considered as brain imaging device, which is called functional near infrared spectroscopy, or I can say FNIRS device in short. So this is a kind of, I can say that this is, a brain imaging device. That means it is basically, it is not directly collecting the brain signals in amplitudical form. In EEG device, it is basically, collecting the amplitude or the signal voltage, which is basically generated inside our, scalp. EEG works in that manner. But here, in the contrary, FNIR is this functional near infrared spectroscopy that basically works on the principle of spectroscopy. This is not basically, capturing the electrical voltage inside our brain. So how does it work? Let's see this. See, inside this box, you can see that this is the data acquisition system, which is the FNIRI's device, right? And this is a, data acquisition system where you have that particular amplifier and which is the processing, the compartments to give you the ASCII codes and give you the, all the graphs and everything. But the sensor part is this. This is the FNIRS band where you can see that this is a 14 channel FNIRS band. Channel in case of EEG device, we know that those channels are the EEG sensors. Here for FNIRS, channels are the combination of the source and detectors. You can see here that these five and these five, which basically resides at the two edges of this band, these are the infrared light sources, right? I'm sorry, infrared light detectors. And in between these two edges, we have four infrared light sensors, right? So you can see that these yellow, this sensors, those are infrared light sources. So these are the sensors, these are the detectors. And altogether, the sensors and detectors are called channels. So we have got the 14 channel FNIR sensors here. Now, how does this particular FNIR system works? You can see that whenever inside our brain or anywhere, basically some kind of neuronal firing occurs during any cognitive task. One thing, one cautionary warning must be associated with this FNIRS machine, that this particular machine or this particular band you cannot place if you have any hairy region. That means you have a restriction for placing this particular FNIRS band you know on your directly on your head. You have the separate kind of FNIRS machine for that, where you can get a separate FNIRS head cap, and you will have a particular position to basically select your to capture the brain images. But if it to basically sense whatever be the cognitive process you are you are creating inside your basically brain, that for that you need a non-hair region. So if it is a band kind of situation, if it is this band, we need to place it on our foreheads. So basically what happens that on our foreheads, it gets some kind of tissue. And over the some kind of tissue, these sources and detectors are basically placed. So if you go through the principle of spectroscopy, you can see that different molecules absorb different wavelengths of in electromagnetic radiation, right? And it basically scatters at different another wavelengths as well. So basically this in this manner spectroscopy works. Here also, in case of functional near infrared spectroscopy machines, the molecule of concerns is here the hemoglobin. Hemoglobin means obviously which contains hemoglobin, that means the molecules which is basically present in the red blood cell, right? So now what happens that these FNIRs always try to measure the oxygen concentration in this hemoglobin, which it can term as oxyhemoglobin, oxygenated hemoglobin. And also it tries to measure the deoxygenated hemoglobin. That means the oxygen, the hemoglobin where basically the oxygen does not present. That means what? That means it tries to figure out whenever there is a certain cognitive process, you know, is going inside the brain, it tries to locate the brain region through this, through this IR light sources, so that it can detect that this particular point is, creating oxygenated hemoglobin, because this particular point is actively participating in the particular cognitive task. Suppose during the mental maths, these particular region, this total particular region, let let us consider that this particular region is not taking active participation in the particular cognitive process, as compared to the, the region which, lies here. So that means what happens? That means you are getting more oxygenated blood here in comparison to this particular place. And you are getting more deoxygenated hemoglobin here in comparison to that. And how does, how can you, detect this? How can you, measure this? You have IR light sources here. So it is being said that light sources, IR sensor, light sources through this IR sensors that can penetrate more if there is more amount of oxygenated hemoglobin. And it is, that means automatically the scattering from that particular source and which is coming back to the detector, that portion is less, because the more amount is penetrating, right? So whenever you have less amount of, oxygenated blood, that means the more amount of deoxygenated blood, then it basically there is less penetration of this IR, infrared light from the sensors, and it is coming back to the detector. So every time detecting and comparing the relative concentration of hemoglobin, I should say hemoglobin means the deoxygenated hemoglobin, and also the oxygenated hemoglobin, by which we have, denoted that particular oxygenated hemoglobin by HbO2 here, and deoxygenated hemoglobin by Hb. So basically, we are going to, every time detect and compare between the concentration of this hemoglobin and, oxygenated hemoglobin for different cognitive tasks. That means for different mental maths, whenever it is given to a particular person or over the persons, when the tissue is in baseline state or in cognitively alert state. So based on that comparison, conclusions can be made that how does this particular person is, experiencing how much cognitive load. So what is that baseline state? Baseline state means, whenever any kind of cognitive task is not going to be performed, whenever your brain is not doing any kind of mental maths, which is an ideal state, which is an, the state where no such, visual stimulus is coming or is popping out on your screen, on your monitor, which gives you any kind of mental maths. So there also, in, I mean, during that period of time also, your brain is liberating a certain kind of signal, right? This is a very calm state of mind. So in that very way, this is called what? The baseline state. Now whenever you are, you are starting your experiment, so automatically after certain stipulated time, one after another, your PPT slides are coming. On every slide you are getting one kind of, mental maths. So automatically your brain must be, actively functioning to that. So automatically your brain is now in a cognitively alert state. So automatically, if you can calculate, if you have a biomarker, if you have a, what should I say, if you have a timer, if you have a biomarker, so you can, easily, segregate that this is my, the time frame where no such kind of, mental maths are going on, and this is the particular time frame where the human brain is cognitively alert and cognitively taking part into the mental maths, right? So you can have two kind of situations, and for these two situations, you can have the comparison between the relative concentration of the oxygenated blood and deoxygenated blood all over this area, all over this area, mind it, because you are tying this Affinit's band, on your forehead, right? And you will have these 14 channels, right? 14 channels. Out of this 14 channels, you will have four, IR sensors, and here at these two sides, you are having 10 detectors. That means each channel, is receiving or is giving back to you through your monitor, that obviously, using that software which is embedded with this particular, FNIR's device, that is the Kobe Studio, software. So using that software and installed on your PC or on your certain kind of, laptops, this all this each and every channel is giving you that particular, two lines or to the comparison between this oxygenated hemoglobin and deoxygenated hemoglobin concentration. So how can you measure? How can you detect? For each channel, you are getting this kind of scope. We call it as voxel. We call it every such this black colored scope, we call it voxel. So for each and every channel, you are getting this kind of voxel where you can see the, the relative change in, uh, oxygenated and deoxygenated, hemoglobin concentration by certain graphs. So this is your work panel, I can say, which gives you the hemoglobin concentration, through the Kobe Studio software. Whenever you have got this, you also, you are now ready to acquire the brain states. So this is how we, perform the experiment. And you can see that here, basically in the front of this, subject, this particular girl is, you know, tying this particular, this FNI's device, so automatically this particular girl is now watching to whatever be the, mental maths that is popping, out on her monitor screen. So I am taking here, those three examples which we have just, solved, a little bit earlier, so that each and every, just to give you the impression that these are the, the situation which basically, coming in front of her, and the, FNIRS band, through this FNIRS band, the basically the hemoglobin and oxyhemoglobin and deoxyhemoglobin concentration is going to be recorded. And what should I say, that during this process, we have 14 channels. So I have just told you that these 14 channels, can be appeared as 14 voxels, as well as, if you can recall that at the very beginning of the FNIS device, I have mentioned that this is also, this acts as a brain imaging device. That means it can provide you the brain image. So what does this image, contain? This image contains the hemoglobin or I mean the oxyhemoglobin or deoxyhemoglobin concentration, concentration level as a brain map. That means as a brain map from these 14 channels. Fine. So how does this particular brain map looks like? You can see this is the brain map. That means this is the oxygenation levels recorded from 14 sensors. You can see, if you can see the, the topmost scale of each and every strip, you can see that there lies the number 0. This is the 1, this is 2, 4, 6, 8, 10, 12, and 14. So this is all this numbering, just point out those 14 sensors, what you are, what is, involved inside this, if an iron is banned. And you are getting, this kind of oxygenation levels, whenever during the task, during the, that particular time frame. Now, if you can closely observe this, the right side of every strip, you can see that there is a 30.2, this kind of, value. Whereas that means automatically it is, you can see that this is a kind of, yellow kind of, color basically represents that high positive value. And whereas the blue and the purple, this kind of region, I mean the bluish region, is having the more negative value, which is the minus 19.1. So it will give you the sense that, you know, you know, near about which sensor or which detector, that means which channel, I can say, the more cognitive, I mean those particular point of the brain region, inside this, whole skin or whole tissue, those are basically, taking active participation during the mental maths. Or there are certain regions, you can see that here, that is the, sensor number, you can say 5 to 7. you know you can see that here you are getting this kind of, blue and purplish, region, where this is not getting exactly, you know not getting any kind of cognitive participation during the process. So here this is an inactive action, that means the baseline state, I have told you, that means no such kind of, mental maths is coming, in my screen. Now if I now go on performing the experiment, and if I now go on, finding what could be the oxygenation level during the easy mental maths, you know computation, then I can say that, you can see that this bluish purple region, is getting a little bit, a little bit smaller, right, a little bit smaller. And also, whenever you are not performing anything, you can see there is a very bright, a kind of, yellowish region, because you have no cognitive load, right, you have no cognitive load. Now you are going to give a little bit stress, right, whenever you are going to perform. So you can see that this yellow bright portion is also, going to be less. That means what? That means the oxygenation level, whenever you are stress free, so then you are getting this kind of value. So whenever you are having this kind of, a kind of, stress, a kind of, mental maths, so the values is also, going to be changed. But you can see that the value of the inactive region is not changing much. There is a change between the, the in the active region. So automatically you will get different kinds of oxygenation level, which gives you the sense that, the particular, voxels, I can say, or particular regions near one voxels or near that particular channel is taking, active participation, that means is highly alert, or is medianly alert, or you can say is moderately alert, or is it a quite inactive state. So I can comment on that, and you can see that if, whenever we are going to increase the difficulty level, whenever we are going to, you know shifting the particular level of difficulty of mental maths from easy to moderate to hard, you can see that this bluish purple region is slightly, is gradually disappearing. So basically, there, for the hard part, for the, hard mental maths, there can be, no such kind of, region which you can term it as, inactive part. The whole 14, 14 regions, I can say, which are associated with 14 channels, you can see that are taking active, participation, because there is some, very, very higher cognitive, task is performing, or task is going on inside your brain. So whenever you are getting a kind of oxygenated and deoxygenated signals, what I have just mentioned you, that I have different voxels, and each voxel gives me a kind of uh, you know graph of oxygenated and deoxygenated hemoglobin concentration. So I can term it as oxygenated and deoxygenated signals as well, because it is giving me one you know beautiful curve. So you can see here that this is a kind of processing where we are getting some kind of noisy data, because we know that whenever we are getting this kind of raw signals, or raw signals, which basically pointing out at particular cognitive task from this FNIS device, first thing, for any brain computer interfacing experiment, we need to denoise that signal, we need to filter it out, right? So inside this Kobe studio we have inbuilt filter as well, so we can perform the filtering action or as well. And you can see that this is a kind of noisy signal, where you can see that there is a slightish pinkish orangish colored signal, right? And another is greenish kind of signal. So pinkish orangish, there's this kind of colored signal is basically the oxygenated signal. That means more oxyhemoglobin concentration is present in that particular signal. Whereas in the green signal refers to the deoxygenated signal. That means the less amount of oxygenation and more amount of deoxygenation, I can say. So these are the signals. And if you can denoise this particular signals, then you will get a kind of this kind of signals. This is a smooth one, so that you cannot have that much of ag points inside in the particular signal. So if you get this kind of smooth signals, so then now you are having the signals ready for further processing, that is the feature extraction, that is the classification, and finally confirming what is going to be the cognitive state. So this is a denoised signal or filtered signal, both in oxygenated, both oxygenated and deoxygenated ones. Now, if you need, this is a graph sign, this is a graphical representation, fine. So now you can be saying that, see, in case of this kind of processing, signal processing technique, obviously we should you know we should get some kind of ASCII value. And that is what I have told you, that we can extract that particular ASCII value, with which we are going to process that particular the signals further with our artificial intelligence or soft computing techniques, where you can see that this is a kind of sample data which we get from FNIRS device. And you can see that this is the voxel 1, this is the voxel 1. That means for each voxel, I'm getting three this kind of rows. So what are these three kind of rows? See, for whenever we are going to perform this particular, experiment using this FNIRS device, then we can select three, we can select the three kinds of wavelength of that particular IR sensor of this light. One is raw, this 850 nanometer, one is ambient one is raw 730 nanometer. So by following each and every, if you change the wavelength of this particular uh, IR light, so you are getting different kinds of values, different kinds of oxygenated values. This is a Excel sheet of the oxygenated signal concentration. And you can see that here the basically the time frame, the time stamping, I can say that the baseline has been started. And obviously following by this particular time stamping, we are getting the different values of oxygenated signal coming from the voxel 1 for three distinct wavelengths, right? After this third column, whenever I'm, in fact, if I consider this is the first column, which is the time, then after the fourth column, from the fifth to seventh columns are giving you the voxel 2 values. That means the oxygenated signal values, oxygenated hemoglobin concentration, I can say. coming from the voxel 2 for these three distinct, wavelengths. And this will be go on, and it will be followed, for the rest of the Excel sheets. So this is how data are going to be extracted from FNIR's device. And whenever we have extracted the data and we have filtered it out, now we are going to extract the features. So what is the feature extraction techniques? I'm not going into it because we have discussed, lots and lots of it. So basically, you know, I should say that apart from the existing features and apart from the known features, what we have talked about in case of EEG signal processing in my last two sessions, here the case I am going to find out the suitable features. I'm going to find out, because see, every time feature extraction is a very important part of any kind of brain computer interfacing, because we need to select or extract right features, right? So we need to extract the features, we need to select the features in right manner so that it can give me the comparison result between the oxygenated hemoglobins and deoxygenated hemoglobins concentration. So keeping that in mind, I can form a particular set of features which I have taken for further processing, and that is the mean values of the oxygenated hemoglobin concentration, mean values of deoxy HBr means deoxygenated hemoglobin concentration, mean value of the combined value of HbO and HbR, so that I can make some kind of permutation and combination to basically generate more and more features, so that my experiment or my result does not get biased. We can have a handful of features, so that we can you know use every kind of features to get the correct result, to get the desired result unbiasedly. So again, the mean value of HbO minus HbR concentration, and also the standard deviation of this combination of these two, standard deviation of the difference of these two, and average slope of this concentration. So I have taken these values from this particular data set, the filtered FNIS data, I can say, and I treat them as my feature sets. So I have got the 7 feature sets of each and every set of mental maths. One is associated with easy, another is associated with medium, as a third one is associated with hard, for the 25 subjects, right? So I have got this much of data sets, and on each subject it is basically performed for 15 times. So I am get a large data sets from where basically we can extract the FNIR's features. Now, whenever we have got that features, we can now use any kind of classifiers. I have talked about much classifiers about the neural network one, the fuzzy one, the initial stage. I have talked about the fuzzy classifier. In the second stage, I have talked about the neural network classifiers. So basically, here we have used a fuzzy classifier, and we have seen that the fuzzy classifier do a little bit good, giving you good result, because there is a kind of vagueness about it, because if in here also we are getting so much nearly located voxels, and we are getting the brain images and the brain signals which are very much nearly located. So that is why we have seen that the fuzzy classifier will give us good amount of results with minimum of misclassification states, where we can form this table, what I have discussed about, that we can form this table by taking those subjects, and we can formulate, or we can tabulate what kind of cognitive load they are feeling by having this cognitive load detection metric, and put it in the order that if I suppose, from if I can scale those things from within 1 to 10, that if I get the metric from 1 to 4, I should say that this is, the subject is having the cognitive load of low level. And if from 4 to 7, we are, indicating that level of the metric that the subject is experiencing the medium cognitive load, and out of the 7 to 10, we are basically indicating that the subject is getting the hard, cognitive level or high cognitive level, I can say. So I can tabulate this kind of table from where this is a, huge list, and from where we are, I have just presented, the results of the four subjects, what we have, observed, that for the easy, moderate, and hard, mental maths related problems, I can see that the subject one is having the low cognitive load for easy, medium for moderate one, and medium for hard one. So I can say that this subject has, an average, averagely it is having a better, capability to balance the cognitive load. Whereas if I see about the subject 2, I can see that for with the easy mental maths, he is experiencing some kind of, metric value which lies, or which falls between this 4 to 7, values, and it is indicating the medium cognitive load. Whereas with moderate and hard mental problems, it is, he is having, a high value of cognitive load. So I presume that this person cannot, balance cognitive load, very well. So we can, indicate that for this particular person that he is having a tendency to get stressed under the challenging environment. So here, whenever you are coming to the subject number 3, and also you can see the subject 4 is exhibiting the similar kind of, results with what the subject 2 is exhibiting. But here, on the contrary, the subject 3 is showing much, good results, where, even if you are giving the easy and moderate kind of sums, the subject is experiencing, the low cognitive load. Whereas whenever the subject is, you know having the, hard kind of, mental maths, it is, having the medium cognitive load. So I must say that about, if I go on looking about this, among these four subjects, I must say that the subject number 3 is having, the best cognitive, balance whenever, he is, thrown into challenge conditions. So if I am the interviewer, so, and if these four subjects, I need to interview, so I can find that this is the subject number 3 is, can take the much lots and lots of pressure and stress, and, during the interview process. So this could be, an application where, interviewer can select or can rank that who are the, the students, this could be very much, applicable to find out the, final year students who are going to, face the job interview, and the MNCs are coming to take the interviews. So basically, they can, rank that these are the students who can deal, in the further time period, further due course of time, that these are the students who can handle much more pressure, where, with the on-site projects, with the client handling or anything like that. So this is all about the cognitive load detection, process, what I wanted to share with you. And thank you so much to listen to my, lecture. And now I'm going to stop sharing my presentation.
Yeah. So, thank you very much, Dr. Saha, for your nice presentation. And so, we are receiving response from the candidates that Priyanka Das has written and very nicely explained. Thank you for informative session. And Mr. Rebak is writing that highly informative and and
Thank you
many
so much.
times,
Thank you so
yeah,
much that
I get
you, all of
communication.
you,
So,
yes, thank
so,
you
so
so much.
now, yeah, so now I will ask the participants that if there is any questions to your microphone, if you have any right now. Participants, do you have any questions right now?
Okay, I am just again giving my email ID, Professor, so
Yeah.
that if they want to reach me, they can reach me. I mean, up to this today, I had the session, so I didn't get so much time to to go through the mail and to answer or to reply or to check mail. But obviously, this is the final session I have in this FDP. So after then, I can get back to anyone if anyone ask